Okay, let's get started on our next mini lecture on general atmospheric circulation. Again, I will reiterate that that I am operating under the assumption that you have already watched the YouTube videos. So, um, some of this is probably our longest mini lecture, um, but I am also hoping to kind of skim through this fairly quickly because you've already watched the YouTube videos, which is touched on everything that I'm going to talk about here. Okay. Okay. So um, we're going to start here with the Earth's orbit around the sun. Again, like I told you, a lot of everything when we talk about the climate system and our circulations, and the next one will be about the oceans. Everything starts with the energy coming from the sun. Okay. Um, and in those YouTube videos, one of the videos should have talked about how the Earth rotates around the sun, but also while it's rotating around the sun, the Earth also kind of wobbles, and so um, it's not like hitting the sun's rays equally as it's spinning around. It's like a top. That little line on the top of the Earth is going back and forth, and that's kind of what gives us our seasons, right? During the northern hemisphere summer, we're tilted towards the sun, so we're getting more rays. That's going to be our summer solstice, and then the winter solstice, we're kind of tilted away from the sun. Okay, so the southern hemisphere is getting more energy than we are. And then during the equinoxes, we're kind of hitting at a better, like a more of a flat surface. Well, not flat because it's curved, but you know what I mean. Like instead of being tilted, we're kind of almost straight up. So all of that sun's energy is going to be directed right at the equator. Um, and when we have the sun directed at the equator, the majority of its energy is going there. And as the sun kind of directs its energy around the globe, that intensity is actually decreasing around it because the light and the direction of that energy is being spread over a bigger distance. So let's think about it this way. One of my favorite ways to describe this is if you imagine like having a flashlight and you are holding like a basketball, right? Any ball, but I'm going to say basketball here. And if you have the light pointed directly at the middle of the basketball, um, it's going to be it's going to make a nice like circle of light, right? If you point it up so that all you're doing is pointing it towards the top of the basketball a little bit, that circle is now going to become more of an oval shape. And the same thing is going to, if it's going to point down to the lower part of the basketball, because as the sun's rays come at the surface of our planet, it's not always hitting evenly in each spot. And this creates temperature differences, energy differences across the globe. Um, this map here is the average annual temperature across the globe. Okay, and these are in degrees Celsius. Just so we're aware. But I don't need you to again memorize all of this, except for that you notice all of the uh, average annual temperatures along the equator there in the black dotted line are much higher than areas more more poleward, let's say. So whether you're just moving away from the equator, whether it's going North Pole, South Pole, if you're moving poleward, you're getting cooler, right? Cooler average annual temperatures. So this creates an imbalance across the planet. Um, this imbalance is not really an equilibrium, right? And the planet doesn't really like that. It wants to kind of balance itself out. And that creates a generalized circulation from the equator to the poles. Okay, so you have the, you know, air at the equator that's full of heat is rising, being pushed up into the atmosphere, cooling, and then coming back down at the poles, right? So that cool air at the poles is being pulled down on the surface back to the equator, creating a nice big circular system. Okay, this this is actually what's happening though, because unfortunately, it's not that simple. And so at the equator, uh, we have still that same warm humid, I'll say, warm, humid air rising. It's precipitating, it's cooling as it rises. And as soon as it rises, it's falling back down at about 30 degrees north and south. And when it comes back down, it's actually drying out and warming. And that's why around 30 degrees north and south are where our world's deserts are, is because you have a general circulation, general movement of air across that latitude that's drying out the region. Now, as we continue going poleward, that air moves. That warm air is going to want to rise again, and again, cooling, precipitating. And as it hits the tropopause, it's going to cool and come back down on the poles. Okay, so we're having basically this a total of 6 cell system that's generally going up, down, and then up, down, and then up, down. And this is what creates different regions of high and low pressure. Because if you remember from our video, one of our YouTube videos, when you have lots of warm air, and especially in that water example, it's going to want to rise. And when it rises, that's low pressure because there's less pressure being put down on the surface because the air is moving away from it. And then as you go into the subtropical high area, you're getting higher pressure because there's air being forced down onto the surface. And so what it looks like is this. We have low pressure at the equators, high pressure at 30 degrees north and south, and then low pressure again at 60 degrees north and south, and then high pressure at the poles. Okay? And actually, I'm going to go back real quick, just because I also wanted to point out it says at the equator the ITCZ, and I just want to define that for you. It's the Intertropical Convergence Zone. And we call it that because that's where the tropical convergence is happening. It's not like on a nice thin line. It's a little bit of a zone, and I'll get to that here in a second. But going back to this diagram, we have all 3 of those cells in the northern hemisphere. They're the same in the southern, are labeled. So the Hadley cell is the one moving air from the equator to 30 degrees north. The Ferrel cell is moving 30 degrees to 60 degrees, and then the polar cell is 60 degrees to 90, the North Pole. And at each region, those purple arrows are representing the general air movement at the surface of the planet. And you can see between 0 and 30 degrees, there's easterlies, right? So the wind's coming from the east. We describe that as an easterly wind. In the what we would call the mid-latitudes, which is between 30 to 60 degrees, they're westerlies. And then it goes back to easterlies at the poles. And you can see across the globe, it mirrors itself, right? So between 0 to 30 degrees north and south, the air is easterly. 30 to 60 north or south, it's a westerly. So this is kind of happening across the whole globe. Now, you might ask yourself, well, why do we have these different movement? And it's all about the Coriolis force. So the Coriolis force is what we call an apparent force, and it's derived from the movement of the Earth. So this kind of conceptual. Again, I'm not going to make you remember all of the details of this, but I want you to conceptually understand if you have an airplane flying in the air, let's say along that green arrow that's moving from north to south, you have an airplane moving from the northern latitudes towards the equator. If an airplane takes off, it's moving in the air and the Earth is still moving underneath of it. So the Earth is still rotating. So it creates an apparent force in how we move in the atmosphere. Okay, that's why airplanes, when they have the paths on the maps that look really nice and pretty, it's always a little bit of a curve because they're also accounting for the fact that the Earth is moving underneath of it when they make their flight plans, right? So the air is doing the same thing. And when the air hits the surface at 30 degrees 30 degrees north and south, and it starts to spread out, that spreading action is impacted by the movement of the Earth, and it turns it right in the northern hemisphere, and then left in the southern hemisphere. And so it's, like I said, an apparent force, but it makes it turn in our view, from our viewpoint, to create these different general wind patterns at the surface. And here's another example. This is kind of a more full view, a bit more complicated, but that's because it has all of the cells labeled here, as well as the type of air and how that's mixing. It has the surface winds also mapped out there. You have the trade winds, westerlies, the polar easterlies. So yeah, that's kind of one piece of this. Now, like I said, we were operating under the assumption that the equator is getting most of the sun throughout these diagrams. And like I said earlier, this is what's happening throughout the year. Our seasons are changing. The sun is going and is more intense in each hemisphere at different times a year. And this is kind of what that looks like. So during the summer solstice, the northern hemisphere is pointed towards the sun, is getting more intense energy from the sun. And in the northern hemisphere winter, the southern hemisphere is getting more intensity from the sun. And if you think about that, if the intensity is changing from the northern hemisphere to the equator to the southern hemisphere and back, and the equatorial tropical zone, that intertropical convergence zone, even I'm getting confused by these acronyms, the intertropical convergence zone, if that's going to be in the area of the most intense heating from the sun, then by that logic, it would shift. Okay? And we can see that in our global average temperatures, right? So instead of looking at the global average temperature throughout the whole year, if we look at it during certain months of the year, right? So these are the averages in January. So we could call it the January normal. So remember, we talked about that in our first mini lecture. And then in the July normal temperatures, you can see that the warmest, the highest temperatures on the globe are shifting between 30 degrees north and south. January, the warmest region, is actually going to be about 30 degrees south. And then in July, it's going to be around 30 degrees north in the northern hemisphere. So that means our ITCZ is moving up and down throughout the year. It's never directly on the equator. It's kind of wavy, like in this image here. And this is important because not only do we get these general flows from these from the sun affecting the weather and like affecting where the weather's coming from, this intertropical convergence zone is also impacting some weather phenomena. And in this example here, we're showing the South Asian monsoons. So monsoons, although typically associated with a rainy season, it's actually just a change in general circulation in a certain region, which means there's a dry season and a wet season. So it's actually the combination of the two that makes it a monsoon. And during the northern hemisphere winter, right? So I'll just call it winter here. During the winter time, the ITCZ is moving towards the southern hemisphere, towards 30 degrees south, which means that Hadley cell is shifting, and the winds are going to be more northerly over South Asia, and that's going to actually be bringing drier air. Okay, and then in the summertime, and drier air means drier weather, less rain, and then in the summertime, that ITCZ is moving north up to about 30 degrees north, right? And now the flow is southerly, coming off the Indian Ocean. And that flow is much more humid and unstable. It has a lot of moisture and a lot of heat. And in that case, you're actually going to get more rain from coming off the ocean, as well as having the ITCZ, because what happens along the ITCZ, you have air rising and you're getting a lot of rain over that region. So this is the kind of process that's happening with all monsoons. So even the one that we have in the southwest US and Mexico, those monsoons are the same kind of a process. And this is what that looks like from a high-low pressure situation. So when that ITCZ moves towards the south, high pressure sets in because you're having more downward airflow because the ITCZs move south. So that circulation's now going down over their region, and that's drying out all of those countries. And then in the summertime, when it moves north, you're getting air rising over the ITCZ, and that creates a low pressure system there. Okay, so those are our monsoons. That's the last little bit from the air circulate or the atmospheric circulation section, and I will see you in our last mini lecture. Okay, thanks, y'all. I'll see you next.